On our previous lesson, we have learned angular momentum, and torque. I'll remind that angular momentum is equal to vector product r, radius vector r, and vector of momentum p, and the torque or moment of force is equal to r, radius vector multiplied by force. And let's find the connection between these two values. Let's find the connection between them. Between these two values. Let's try to find a derivative from this value, from its left and right sides. This derivative will be dl by dt, and this will be derivative from this vector product, and this will be equal to here I will use the rule of calculating of derivative from product. From calculus, from differential calculus, it will be dr dt multiplied by momentum and plus vector r multiplied by dp and dt. Okay, and what can we do with this? First of all, we can remember from kinematics that derivative of radius vector is equal to velocity, and momentum is equal to product of mass and velocity, this momentum. And what about derivative of momentum? It is equal, according to the second Newton's law of motion. It is equal to force F. So let's use all this formula here. We'll get mv velocity multiplied by v and plus radius vector r multiplied by f according to the second Newton's law of motion. So here we have vector product of vector v by vector v. And as you can remember from analytical geometry, such vector product is always equal to 0. Because when two vectors have the same direction, the angle between them is equal to 0, and in this case, their cross product or vector product is always equal to 0. So this will be 0, and according to this definition of torque, this will be equal to m. M is torque or moment of force. So this will be equal to m. Okay, so from here we have got the connection between angular momentum and torque. So what can we write? Here? We can write that connection between connection between angular momentum and torque. So we have got that change of angular momentum or derivative from angular momentum is equal to torque or moment of force. And what will be in case of rotation around the fixed axis? In case we can rewrite this in some another way. It will be dLz divided by dt, and this is equal mz. It will be in case of rotation around a fixed axis. This is practically important case that we will get often. And so what we can do, we can write this we can write these two equations that define connection between these two dynamical values from dynamics of rotational motion of perfectly rigid body. Okay, do you have any questions about this?
So far, so good, teacher.
Okay. So let's continue. In this case, let's continue. Let's define more particularly angular momentum. Let's have a look at angular momentum. According to the definition, I'll draw a picture again. If we have axis of rotation z, and radius of rotation of material point, radius r I. Here we have the right angle, and if we also have angular velocity omega, and angular momentum will be directed in the same as axis of rotation, L I z. Liz is angular momentum of material point indexed with I. And in this case, linear velocity or simple velocity of this material point will be directed from us to the screen. It will be from us to the screen. This is velocity of point I. Okay, in this case, according to our previous lesson, angular momentum of point I is equal, according to related to the axis z. Angular momentum related to the axis z is equal to r I, vector product r I, multiplied by momentum of this point. And as we can remember, momentum is equal to product of mass and velocity v. We can see this here. It's product of mass and velocity v. So we can rewrite this equation in the next way. Product of mass and vector product of Ri and Vi. And now it is necessary to remember kinematics. We can remember that linear velocity connected with angular velocity by the formula. That Vi is equal to vector product omega angular velocity and radius Ri. Radius Ri. So here we can use this formula and we will get m multiplied by double cross product. This double cross product R and omega and Ri. Here double rectangular brackets here. And what to do with this? We should remember formula from analytical geometry for double vector product. We have such formula from analytical geometry: A, B, and C vectors. And this vector product may be written in some simpler way. It will be B multiplied by A by scalar product N and C. Scalar product, what is the same as dot product, minus C multiplied by A B. This formula may be easily proven if we rewrite left and right parts of this formula in components of vectors, and in this way we will prove this formula. This formula is from analytical geometry. We can use it here. And we will get from this m omega A and C R and R Ri and Ri and minus m R I and multiplied by scalar product of Ri and omega. Ri and omega. And what can we say about this scalar product? M, it is necessary to write with index I, because this is mass of defined material point. This mass of material point with index I. So it is necessary to write this lower index. Okay. And the dot product of vector by itself is equal to absolute value of this vector to the power of 2. So this will be mi and ri to the power of 2 and omega. And what about second term? We can see that angle between ri and omega is 19 degrees. So vector omega and ri are perpendicular vectors. And in case when vectors are perpendicular, their dot product is equal to 0. It is also from analytical geometry. So what do we have from here? What do we have? We have that angular momentum of material point of perfectly rigid body which rotates around a fixed axis is equal to mi ri to the power of 2 omega. And this may help us to find angular momentum for a whole rigid body. This angular momentum will be equal to sum of all angular momentums of all points, and this will be equal to mi ri to the power of 2 omega. And angular velocity is the same for all points of rigid body. So we can write this in brackets. And this value in brackets is known as moment of inertia. So this is equal to Iz, moment of inertia. Moment of inertia. According to this definition, moment of inertia is equal to moment of inertia. Sorry, it will be moment of inertia related to an axis. Related to an axis z. So it will be Iz is equal to sum of I m I r I to the power of 2. This moment of inertia. Or in case of solid body, solid body, we know that it consists of infinitely amount of material points. So in this case, we have integral instead of this sum. So in case of solid body, we have to rewrite this formula with integral. Maybe you familiar with such integrals from your calculus course. So here we have integral r to the power of 2 dm, and this is the same as triple integral along the whole volume. Rho is density of rigid body, and dv. This moment of inertia related to an axis. Okay, so what questions do you have?
For what?
Okay, and if we use this definition, we can say that angular momentum of rigid body angular momentum of a rigid body related to a fixed axis. Related to a fixed axis. So it can be written in easy form with moment of inertia. So we have LZ is equal to I moment of inertia multiplied by angular velocity. Angular velocity around axis z. And because of this, I have written lower index z to notice that this is velocity and angular velocity around axis z. Okay, and it is necessary to clean some place on the screen. And we'll have so we have such a formula, and let's substitute this formula here. In this case, we have we will get we'll get that we'll get that we'll get that I z d omega z by dt, and this is equal to torque related to an axis z, related to an axis z, or if we remember kinematics, this derivative is equal to angular acceleration. So we can write or iz multiplied by angular acceleration around this axis z, and this is equal to torque related to axis z. So this is law of rotation dynamics around a fixed axis. So this is law of dynamics of rotation of a rigid body around a fixed axis. Around a fixed axis. Around a fixed axis. Okay, so what questions? Which questions do you have? Or what questions do you have about this?
Nope, teacher, everything's fine.
Everything fine. Okay. Okay, and let's consider one special case. When torque is equal to 0. If torque is equal to 0, we'll have that this value or this value or this value is equal to 0. And if derivative is equal to 0, we know from calculus that in this case function is constant. And when derivative is equal to 0, the function is constant. So in this case, we will get the law of conservation of angular momentum. Law of conservation of angular momentum. If law of conservation of angular momentum, if m is equal to 0, then in this case if m is equal to 0, then according to this, L, angular momentum, will be constant. And L is equal to constant. L is equal to constant. L is equal to constant. Or for rotation around the fixed axis, another case of rotation. This another case is more important for us than just general case of rotation. So in this case, we will get that I'll just rewrite this, or if m related to an axis LZ and is equal to moment of inertia IZ and omega Z. So here, law of conservation of angular momentum. Law of conservation of angular momentum. Law of conservation of angular momentum. Okay, and let's consider some interesting device that is known as gyroscope. This device is often used in the different multimedia system. For example, for stabilization of orientation of video camera. If it is necessary to fix its direction in space, gyroscope may be used. So let's consider in this case a gyroscope is some massive rigid body that rotates with angular velocity omega. And in this case, angular momentum will have the same direction as angular velocity. Has. So LZ, angular momentum related to the axis of rotation. And let's impress some torque on this. But the direction of this torque will be perpendicular to the axis of rotation. This is case of gyroscope. In case of gyroscope, torque is perpendicular to axis of rotation. And what will be in this case? According to this equation, angular momentum will change. But according to this law, direction of increase of angular momentum will be the same as direction of torque. So according to this, we have that the direction will be here. This is direction of increase of angular momentum. So it is dLz. And as a result, we will get new angular momentum, LZ plus dLz. dLz. So what is the connection? What is the connection between these angular momentums on this picture? The connection is may be defined from this angle. This angle is known as angle of precession. D phi. We will sign this as d phi p. And if here is the right angle, and d phi p is the infinitely small value. So we will have in this case that dLz is equal to LZ multiplied by tangent of d phi. But d phi is infinitely small, and in this case tangent is equal to this angle. So we have such equation d phi p, and we can get first derivative from this dLz dt is equal to LZ d phi p and dt. So what do we have? According to this equation, derivative of angular momentum is equal to torque. So this will be torque M. This will be torque. And according to the kinematics, derivative from angle of rotation is equal to angular velocity, omega p. So this may be written as m is equal to omega p omega is angular velocity of precession. LZ. And we can also remember that angular momentum is may be written with moment of inertia by this formula. So we will get IZ omega p precession and omega z. Angular velocity of rotation. Angular velocity of rotation. Okay, and what is the direction? What is the direction of omega p? The rotation of this axis, is here. So according to the right hand rule, angular velocity of precession will be directed from the screen to us. So here, this is angular velocity of rotation and angular velocity of precession. And to get the right directions, we may write this formula in vector form. So we have angular velocity of precession, omega p multiplied by Lz is in vector form, and it is the same as moment of inertia multiplied by vector product omega p and omega z. Okay, do you have any questions about this?
Give me a second. Yeah, it's fine, I think.
Okay. Okay, so I will clean some place on the screen, and we have got some formula for gyroscope. Gyroscope this is a device that is often used in different in techniques, and especially in multimedia systems. For gyroscope, and where omega p is angular velocity of precession. Angular velocity of precession. Angular velocity of precession. Is angular velocity of precession. Angular velocity of precession. Okay, and here we have a moment of inertia, and from this formula, it can be calculated. Using triple integral. In general case, it will be triple integral, but in some simpler cases, it may be some simpler integrals. So let's have a look at one example. A homogeneous rod. Moment of inertia. Moment of inertia of a homogeneous rod, moment of inertia of a homogeneous rod related related to an axis Z of a homogeneous rod. And what is a homogeneous rod? I will draw a picture. And draw a picture. This is a homogeneous rod. Homogeneous rod. Axis of rotation will be here. Axis of rotation Z. The length of this rod is equal to L. Length of this rod is equal to L, and here the half of this length, L divided by 2. L divided by 2. L divided by 2. And how to calculate moment of inertia of this rod? First of all, we may define linear density of this rod. Linear density, if rod is homogeneous, will be simple, m divided by L. M divided by L. And if we have simple rod and linear density, we will get just simple integral instead of a triple integral. In this case, we have just simple integral. So this dm is equal. So dm is equal to lambda dr. Lambda multiplied by dr, and this is the same as m divided by L multiplied by dr. So it will be m divided by L integral r to the power of 2 dr, and integral limits according to the picture. Integral limits will be from minus L divided by 2 to L divided by 2. And from here we have m divided by 3 L r to the power of 3, and limits from r is equal to minus L divided by 2 to r equal to L divided by 2. So we have m divided by 3 L, L divided by 2 to the power of 3 minus L divided by 2 to the power of 3. And after simplifying, after simplifying, we have m multiplied by squared L divided by 12. This is a moment of inertia of a homogeneous rod around related to the axis z, related to the axis z. Okay, do you have any questions? No.
It's okay for me.
Okay. Okay, that's great. That's great if it is okay. That's great. So we have formula, and we can use this. When we are doing exercises. We can use this to do exercises. So here we have. I'll make this in blue frame because this is just a useful formula. But this is not a fundamental physical law. It is just a useful formula. And the next useful formula is moment of inertia. Moment of inertia of a homogeneous cylinder or a disk related to its axis of symmetry. Related to its axis of symmetry. This may be written, drawn as this. Oh, it's not okay. Oh, now it is fine. Radius r. Radius r. And without proof, moment of inertia in this case will be iz, because we don't have enough time to prove everything. But it can be proven with double integral. In this case, we have double integral that may be reduced to simple integral. It may be reduced to simple integral. Moment of inertia of a homogeneous cylinder or a, I have written of course, or instead of, or a disk related to its axis of symmetry. Related to its axis of symmetry. related to its axis of symmetry. But not red, it will be also blue. Blue frame, because it is useful formula, but not something fundamental. And the last useful formula, moment of inertia. Moment of inertia of a homogeneous homogeneous ball or a sphere related to an axis passes through its center. Center or center. I have searched that center center is American English, but centre is British. Sometimes British and American English are different. In some cases, they are different. But formula will be the same in both cases. Iz is equal to 2/5 of m r to the power of 2. It will be 2/5 of mr to the power of 2. mr to the power of 2. Okay, what questions do you have?
I don't have.
Okay, and what should we do? What should we do if we have to find a moment of inertia related to an axis that doesn't pass through the center of mass? Of course, we can use general formula and use integral, but it is not convenient. We have simpler way. We have so-called parallel axis theorem. Parallel axis theorem. It's a pity we don't have enough time to prove this, so I will just write this parallel axis theorem. Parallel axis theorem. Parallel axis theorem. According to this theorem, moment of inertia is equal to moment of inertia related to an axis that passes through the center of mass plus mass of rigid body multiplied by distance between these two axes. And what do we have here? What do we have here? I0 is moment of inertia. Moment of inertia related related to an axis. Axis passes through the center of mass. Center of mass. And I. What about I? Is moment of inertia. A moment of inertia related to an axis that is parallel to an axis passes through center of mass. Through the center of mass. Center of mass. And D is distance between these two axes. Distance between these two axes. A parallel axis theorem. It is very useful. When we have moment of inertia related to an axis passes through the center of mass, and when we have to find moment of inertia related to an axis that is parallel to axis passes through the center of mass. Sometimes this theorem is very useful. Okay, and what more? We have also consider work of torque. Work of a torque. And how to do this? Let's draw a picture. Axis of rotation. Axis of rotation is Z. Axis of rotation is Z. And of course, in this case, moment of a force, or torque is here. For a moment of a torque of material points if M I Z. And let's consider some infinitely small angle of rotation. Infinitely small angle of rotation. In this case, we have angle D phi. This is infinitely small angle. Radius of rotation is R ri, and a vector displacement vector is dr. For point I, it will be dri. And we know that differential of work will be dAi for material point Fi multiplied by dri, or we can consider this as a projection Fi perpendicular, in this case is perpendicular to the screen, and multiplied by absolute value of dri. And in case of infinitely small displacement, this value is equal in this case to the path length. In case of the infinitely small displacement, so we will have. Sorry, here we don't need vector. So it will be Fi perpendicular ds. And we know that ds, path length, may be written as radius of rotation multiplied by angle of rotation, dphi. Radius of rotation multiplied by angle of rotation. And we know from our previous lesson that this is torque. This is torque of material point. Torque of material point related to an axis z. Of course, absolute value. Okay, and from here we may write this work of rotation, work of torque, if we consider all rigid body. It will be sum of works. Sum of these works, dAi. So it will be just absolute value of mz multiplied by differential of angle of rotation phi. So after integration of this, we will get integral of mz dphi. Integral of dphi. Integral by dphi. So this is work of a torque. Work of a torque. In case of rotation around a fixed axis. In case of rotation around a fixed axis. Okay, do you have any questions about this?
Give me a second.
Mhm.
Okay, okay.
Okay,
I can move this.
okay. So we have a work, and what about kinetic energy? What about kinetic energy? We know from previous lessons that kinetic energy of system of material points uh, is equal to sum of products mi vi to the power of 2 divided by 2. And from kinematics we know that this velocity, linear velocity, is equal to uh, angular velocity uh, multiplied by r radius of rotation. So let's use this here. We will get sum of mi omega r I to the power of 2 divided by 2. And from here, we can rewrite this formula. In this way: mi r I to the power of 2 in brackets omega angular velocity to the power of 2 divided by 2. And what about expression in brackets? In brackets we have moment of inertia. So we will get I omega to the power of 2 divided by 2. Or we can write it omega z or e z omega to the power of 2. So we have got kinetic energy uh, kinetic energy of a rigid body rotates around a fixed axis. So we don't have to calculate this sum. We may use simple formula. Kinetic energy is equal to I z omega to the power of 2 divided by 2. Okay, and the last for today will be kinetic energy of rigid body in plane, in case of plane motion. We don't have enough time to prove this. It may be proven in a way similar to this, but but it will take much time. It will take much time because formula will be long. So kinetic energy of a rigid body body in planar motion. Planar motion. Planar motion is motion when material points move in parallel planes. All material points of rigid body move in parallel planes. This is case of planar motion. So in this case, kinetic energy is equal to mv0 to the power of 2 divided by 2 plus I0 omega to the power of 2 divided by 2. And what is V0? V0 is velocity of the center of mass velocity of the center of mass. And I0 is a moment of inertia related to the axis passes through the center of mass. The center of mass passes through the center of mass. Well, this is kinetic energy of rigid body in planar motion. Okay, what questions do you have about all of this?
Also, there's too many equations, too many formulas in today.
Yes.
After the example, it will be more fine.
Okay. We'll have a few examples tomorrow,
Mhm.
I hope.
Mhm.
So I wait for you tomorrow.
Sure.
And now, thank you for your attention and have a good day.
Thank you, teacher. Have a nice day. See you.
Okay.